Hello again. Continuing now with the synthesis aspects of the design process, we're going to talk this time about the post-concept aspects of developing a given design concept, mainly relating to detailed design and prototyping. As I mentioned last time, before actually proceeding to detailed design and prototyping, you would typically engage in some amount of deliberate evaluation of multiple potential design concepts, which are often termed candidates. I'll have more to say later about evaluating design concepts because I cover that closer to when I cover other aspects of design evaluation, such as verification and validation. But for now, just keep in mind that before you would decide to go very far in your development of a particular design concept candidate, there would usually be some sort of careful evaluation done at the concept level. Now, speaking of the concept level, before we get into detailed design, let's just say a few words about this murky term conceptual design or concept design. Like other terminology of engineering design, this can mean a range of things. It's sometimes used as a verb to refer to the ideation or concept generation process itself. It's also used as a noun to refer to any of the various design concept candidates that may emerge from that process. And it can also refer to a particular design concept that is selected to proceed on toward detailed design after that sort of careful concept level evaluation that I alluded to. Another murky aspect of this term is that it can refer to a wide range of extents of development for a given concept, ranging from the very abstract, rough, highly tentative, and non-specific ideas that may be floating around in ideation to something just short of detailed design. And it can also be before or after you may have gone through a sort of structured concept level evaluation step. If it's after, there's also a term preliminary design that's sometimes used. But again, there are no hard and fast rules about that usage. These terms get thrown around in a lot of ways. Also, in software engineering, the term software architecture is often used in a way that's roughly analogous to what is termed conceptual design in many other engineering disciplines. Nevertheless, at some point, we make a decision to take at least one design concept all the way to what we call detailed design. So, what is that? Well, in its broadest sense, detailed design can be thought of as design information that would be sufficient to be able to direct someone to implement the design in a prototype, without leaving room for significant discretion or interpretation by whoever will be producing it. So that means that even if the prototype is being produced by someone who is not on the design team, in principle that shouldn't matter because any gap filling, if you will, should be a very straightforward matter that does not involve any further design judgments to be made. And of course, sometimes that level of objectivity is effectively enforced by the fact that it's a computer interpreting the instructions, such as with 3D printing. Now, a couple points about this. First, when we say sufficient to produce a prototype or sufficient to direct the production of a prototype, that is through the prism, if you will, of what sort of prototype we want at this point in our process. So I'll talk a little later about different sorts of prototypes there are, but with this broad view of detailed design that we're taking, just keep in mind that it could include, it doesn't necessarily imply one of the more advanced or complete sorts of prototypes. So we're defining it loosely through the prism of what sort of prototype we want. Also, remember back when we talked about design requirements, and we talked about how requirement specifications are requirements that don't leave room for interpretation. It's objectively determinable whether they've been satisfied or not. So there's some overlap there with what we're talking about here, because when we talk about detailed design and we say, well, it's sufficient to direct production of a prototype, meaning there can't be significant ambiguity or vagueness about the instructions we're giving and the information about the design. This means that we are needing to refine our design requirements. We do a lot of design requirement refinement in the process of detailed design, but we still might not necessarily have all of our requirements translated into specifications. We hope to by this point, but if not, and particularly if it's not a very advanced prototype that we're doing, we might make the decision to still leave some of those requirements in a somewhat subjective form. So if that's the case, then to whatever extent decisions need to be made to provide those objective instructions or to provide that objectively interpretable information about what kind of prototype we want, we may have to go out on a limb and make some commitments tentatively for purposes of a given prototype. Now, this is where we start to increase the risk of not having translated all of our requirements into specifications. That's going to depend on a lot of factors about budget and timeline and other things that we'll also be getting into. So yes, we hope that as many of our requirements as possible are specifications by now, but we do allow some room for the possibility that they may not be. Something that's typically an integral aspect of progressing along the path towards detailed design is drawings. There's a vast range of types of drawings spanning all the various engineering disciplines. Various drawings can exist at varying degrees of completion and development, depending on how far along you are en route to detailed design. I'll just briefly go through a few examples that really doesn't do justice to the breadth and depth of this area, but just to give some feel for what I'm getting at here. For example, for mechanical designs or mechanical aspects of a design, we generally refer to the drawings as detailed drawings if they depict the parts or assemblies that will need to be made. And sometimes something short of a detailed drawing is called a layout drawing. Electronic aspects of a design typically have circuit diagrams. These are often schematic, which schematic in general means using standardized symbols, and schematics for electronics refers to standardized symbols for that. For software, there might be various types of flowcharts, sequence diagrams, or a range of other possible notations. Chemical manufacturing processes use process flow diagrams or PFDs, and for even more detail, piping and instrumentation diagram. And structural and civil engineers use architectural and structural drawings. And again, that's just a smattering of examples to barely scratch the surface. There are lots of great resources out there about all of those and many more. Okay, so another topic I want to briefly touch upon is bill of materials. For any mechanical or electrical aspects of a given design, the designers will often prepare a document known as the bill of materials. This is essentially a list of all the components that are needed to make the design being specified, with sufficient information that would be needed to obtain all of the correct components in the correct quantities. For mechanical parts, these are typically grouped into parts and assemblies, with parts being the most basic component and assemblies being made of parts. The bill of materials is a document that's often considered part of detailed design, along with any drawings and any written information. And of course, there are variations of the particulars on these, and a simple internet search will turn up several examples. Also, for chemical products, recipes and formulas can be thought of as somewhat analogous to a bill of materials. Okay, now let's turn our attention to prototyping. So, as I indicated earlier, there is a range of types and levels of prototype, and this is true both within a given engineering discipline and across engineering disciplines. So, speaking very broadly now, we can generally think of a prototype as a full or partial embodiment of what we're designing, from which at least some information can be obtained about its ability to satisfy our design requirements. And typically that information is gained through testing or inspection of the prototype. So in a sense, we could think of prototyping as part of design evaluation, since the reason for making them is to determine how far along we are in satisfying our requirements. It's not as though there are always clear lines between synthesis and evaluation, particularly with the more experimental or exploratory sorts of prototype, when that's feasible. In those cases, it can almost seem simultaneous how you flesh out an evolving concept and get quick feedback as you go. And when that is feasible, either because of low costs involved in a given case, or because of suitable simulation software, for example, it can affect how we view some aspects of the synthesis and evaluation related stages. When you consider it a separate iteration of one step or another, becomes a judgment call in these cases, and we can talk a little bit more about that when we get to project management. But that's less important than the substance of it, which is that you ideally want to have quick feedback to be able to adjust your design decisions as close as possible to being in real time. And whatever the means that gives us the ability to do that or increases our ability to do that, that's generally a strong efficiency in the process. So now let's briefly go over some common types of prototype. And again, these are just some typical examples from some major engineering disciplines. They apply to some more than others, and even within any given field, there's going to be a lot of variation. So typical caveats apply, but with that, let's just go over a few of the more common examples. There's what's commonly called a mock-up or a looks-like prototype. This may focus on certain aspects of a design, such as, for example, its exterior, which might be useful if you're focused on user interface, user interaction aspects of something, ergonomic aspects of something, but it does not typically focus on capturing full functionality. A functional prototype is sort of the opposite. It focuses on proving that the functional requirements can be satisfied, even though it may not look at all like the envisioned end product. And oftentimes we'll consider a functional prototype to be a test bed if we're in a situation where we expect ongoing changes in light of the results that we get. So if we realize that we probably still have a ways to go, then in getting a functional prototype that's going to meet all of our functional requirements at a satisfactory level, then we're likely to consider it a test bed. Also, when a functional prototype is limited to a particular subset of the overall functions that are being targeted, it's sometimes called a focused prototype. So earlier I had mentioned computer-based simulation as a potential way to more efficiently blend the synthesis and evaluation aspects, or perhaps expedite small loop iterations between them. Sometimes that's also known as virtual prototyping or computer-aided engineering, CAE, and it can be particularly useful in engineering disciplines or particular types of projects where physical prototyping is very costly or in some cases infeasible. Note that the term model can be used in a range of virtual and physical contexts, but usually it indicates something well short of a fully complete embodiment of our intended design. Okay, the last thing I want to talk briefly about before wrapping up this segment is fabrication for physical prototypes. Prototype fabrication spans a range of skills and subjects, which of course varies by engineering area and type of product. For many common projects, it can involve things like woodworking, sewing, 3D printing, microcontroller coding, soldering, laser cutting, CNC, and various machine shop tools. Sometimes exploratory, early so-called low-resolution prototypes can be fashioned from household items or art supplies. Engineers often enjoy being literally hands-on, but it's also common for engineers to not be the ones who physically fabricate their designs. Even for early prototyping, an experienced technician can often be needed. Also, their input regarding the pros and cons of various possible fabrication approaches and the implications of that for some of your design choices can be quite a valuable conversation to have. And that also gets into design for X, which we can get into later. Of course, to whatever extent you're involved with the fabrication of a prototype, be sure to take all appropriate safety precautions and have all appropriate training. Okay, in the coming segments, we're going to talk about design evaluation. And the first aspect of that we're going to talk about is concept evaluation. See you then.